Welcome to a new test and teardown video. This time it's a Marconi Instruments counter timer TF2415. It is of course Nixie based. Let's get some light in here. I don't know how can I get the light. This is annoying. But 1, 2, 3, 4, 5, 6, 7? Really? So we got 7 Nixie tubes inside this beauty. I just spent about a half an hour trying to polish and shine up the front so it looks really nice and beautiful for the video. So you should be really envy and all that, because I made it look so beautiful. I love it. And did I say, I don't know how many times did I say that, I love Nixie tubes. They're fantastic. So let's open and inspect before we power up. Always a good advice. So let's look a little bit here on the back of the unit, where we can see all the different connectivity. This is some, they call this auxiliary connections with all the different start and stop and whatnot kind of stuff. Some BNC connectors with some external crystal oscillator, and it's a secret what is the frequency. And here we go, 40 watt. That is really good information. And for you guys who wants to try and Google stuff, this 2415, it's just impossible to find any kind of information online. The 2416 is something you can Google, but not 15. So it's special. I think this dirt here and the dirt that we see in this edge here represent a little bit about how it was looking at the front as well when I got it, but I was able to shine it real nice and fine. And this is something you need to look a little bit extra careful about. Look at that. You can see the wires inside the cable here. It's been twisted, and this is a classic short circuit location due to this, and you can even feel it's a little bit dodgy here. So I should probably cut a little piece of the mains cable, but let's go inside and have a little deeper look. Inside the lid we got those annoying sticky, see, they dissolve this foam stuff and turns itself into nastiness, and it's of course all the way in here. So I need to go outside and brush this and compressed air clean and all that kind of stuff. And now we can see the 7 Nixie tubes, and they are really nice and beautiful. We will get a little bit deeper into that in a minute. The fun thing is the first one is connected to some special secret stuff that is in here or somewhere, maybe. I don't know exactly what is going on, but that will of course be the fast counter, right? And all the others, they go slower and slower. It looks like we got 2 modules per readout, and there's even a little, see, a flex board. How about that? So after a little bit of cleanup, now I'm starting to look a little bit deeper on what is going on inside this unit. So just see this thing. So this is the piece of metal that holds down all the circuit boards. And see, the 2 little nuts there stamped into this little piece of metal. And that is loose here on the back. So when you remove the 2 screws, it's going to go flippity-floppity down there. And it's probably also going to be a big problem putting this back together. Why wasn't this done in this piece of metal? That is a little bit dumb. This is the first Nixie counter. Well, no, this is not the first. This is the second. And this one is marked with blue. So it's not the same as the others. So maybe we should take out one of the others and then let's have a look at them side by side. But what I think we got here is the classic transistor binary counter with 2 and 2 and 2 and 2. So we got 4 of these in a set. And then we got a little encoder to make it into a decimal format. And what we got again, this is probably also a decimal driver or something like that, because here we got 8 and now we're driving the Nixie with 10. So there's a lot of funky stuff going on here, the way that it's counting or encoding and all that kind of stuff with all the diodes. And again, I cannot find any schematics, so that is a little bit of a problem. But I really like the way that they have done this. Probably to save time and trouble. And it goes like that. Look at that. Instead of hand wiring all the wires from that socket to the board, this is the way to do it. Isn't that just pretty? And here we can probably better see what's going on. Oh, now I see. Okay. Can you see what's happening here? This is the latch. So that will be the counter, that will be the latch, and that will be the Nixie driving. Now it makes all sense. Oh, this is impressive. So that will be the 2 different versions of counters side by side. So I think this one is running, of course, 10 times faster than this one. And all the others, they are exactly like this. So that is just how it is. There's just this little 4 NAND gates. That is the only difference. And look at that, 67. So 1967 is the year code for that IC. And that will be the 2 next modules again side by side. So they are completely different. So there is a reason why they got different colors. And also the connectors, they are different, so you can't really flip them. And here we got some NAND gates again from 68. I'm not super good with the 3-digit date codes. There's probably a way to figure that out. And here's another one from 68, and then the 3-digit date codes there. That was definitely the first and very old way to do it. And the other one, all the rest, that's just counters. I believe this is counters because we can see the flip-flops and the diodes that goes around here. So it looks a lot like, counters or dividers, time-based stuff like that. And this is, of course, a double-sided. Look at that. And why are we having some tracks that's just going nowhere? What is the purpose of that? And it's the same here. Just some funky tracks, especially this, just going somewhere. And we have them under the, I mean, what the heck is the idea? And also up here. What are they doing? And look at the little varnish dots they put on top of all the solder points, and it's exactly the same on the back side. Look at that. So every time you solder something, oh, you need to give it a little red dot and mark it in the little book and sign it, and there you have it. I mean, really? What is the point? Maybe some sort of a checkup. It's definitely something. This is the red board that was all the way here to the right. And that is also a double-sided board with a little transistor area here. But I think that is crystal oscillator driver temperature controller. And there you have it with some NAND gates again from 67. And green nail polish. How beautiful, super shiny on all the solder points. Please comment with the color on the dots if you know exactly what was the main idea. And I think inside here is where we find the crystal oscillator. It also looks like we got some connectors down here so we can pull out the entire power supply. We just need to figure out what kind of screws we need to release. And maybe we can get the oscillator out as well. And then we have pretty good access to clean all the dust and clean the transparent glass and all that. So it's going to be nice and shiny once I get this up and running again. So what do you think about this type of service-friendly design? You can pull out everything, just loosen a few little screws, see these 3, and then you pull out the entire power supply, and 3 more little here, and then chip chip, out is your crystal oscillator. So I was right about this. Look at that, the beautiful paint job as well. And here you have it. 1 megahertz output, and so it's running on plus minus 6 volts. And what is that? Some 25 volt RMS. Maybe there's a heater and a heater controller and all that kind of stuff in here. And it looks like it's full of isolation material and all the beautiful. That is probably a little adjustment screw. We gotta open this one and inspect that one. And the power supply also super, super nice and beautiful. See, that will be the connectors for everything here. So, I don't know about safety and isolation distances and all that kind of stuff. There will be mains frequency and mains voltage on some of those pins. And there's a pin, but it's still there. I have to look a little bit closer here about the safety for all that. Oh yeah, I saw some really cool things. In the old days, you will find date codes on electrolytics. See, October 67. This one is February 68. And here's a weird one. Where are you? You are gone. You are hiding. Here is one that is a little bit funny. How can this one have December 65 and April 68? That is one weird thing. But I think we're getting really, really close to a build a date or build year for this one. Oh, this is one warm resistor, wouldn't you say so? Yeah, but about the power supply, we even got the full specifications, and we got adjustment points and checkpoints. So what I can do is plug this in alone and then verify all the different voltages here. And then start repairing everything. And oh, we see this? This looks like we have at least a little bit of leakage from that one, see? Yeah. Well. all the soldering on that transformer. And now I also got super good access to this. I need to fix this wire. And they mount it like this, and then it goes, of course, to the switch. And from the switch, there's probably some wires going to the power supply module. Maybe that is what we have, right? Yeah, this looks like pretty good safety. So, okay, so let's see. The bottom view of the entire unit is, of course, super cool. They made some connections here that I don't understand exactly why it's made with those little thin. It's all over the place. Then you have these chassis here, and it's with a big hefty ground that goes all the way through, and this thick white wire is from the mains switch, and it goes this way to the power supply. Here it even says mains, and right next to mains we got low voltage coming out. They didn't even have a free pin for isolation. Really? So we're now inside this oscillator module, and it is, of course, isolated like that. And I think inside this piece of aluminium here we will find a big hefty crystal, and maybe there's a little adjustment here that you can access from the outside. So that tells me maybe the whole oscillator is in here somehow. And then the windings we have here, if we look here, see, it looks like that will be the heater windings. They're just connected in parallel. And we've got some other wires here connected to some tiny little, look at that, a temperature sensor. So those wires here, that will be the temperature sensor and regulator system, and it goes all the way in here to all this. So I believe all this here is just temperature regulation and all that kind of stuff. And here is a over temperature test check something, and it's a little relay that moves with the temperature here, and everything is heated and isolated, including the regulator and all that. I think that is quite a beautiful design. I would love to try and have a little look in here. Maybe that is easy. I don't know. The wires here maybe prevents me from opening, but let's give it one little try. Maybe you can see how dirty the glass is here, and I really want to try and clean it. I also want to try and clean the front of this Nixie tube. So how do you pull these out? Here's my little go-to solution. Take some gaffer tape and then put it around the tube like this. And there you have it. Now I can grab it real good, and then I can easily do the little wriggly like this and get it nice and safe out of the socket. Look at that. Pretty smart. Then this works with all sorts of tubes in hard to get places. Of course you need to fold the tape so it's non-sticky on the outside, right? It's really dirty. Numicata. Ooh, this one is there. Wow. This is the one that says megahertz and kilohertz and seconds and this and that. Oh, this is nice. So this explains why this one is connected to the switch to do the different indications and whatnot. All right, I love it. So let's try and see what happens We got mains connected, and it seems to be at least a little bit alive. We got high voltage running, and we should push reset. Yes. I don't see any. Yes, there is a gate blinking. So what if I input a signal, just 1 kilohertz? Will it automatically? Yeah, look at that. We got 1 kilohertz. So what about if we say 1, 2, 3, 4, 5, 6? Okay. Okay, so it's 1 off at the last digit. It looks like we can do a lot more. Let's try the different. Oh, this is point. Oh, I think maybe there's something here with. Here we go. Much faster, right? So this is the fastest. And there you have it with the megahertz. Isn't that just lovely? They made this with a Nixie tube instead of all sorts of LEDs or pre-written messages here that just light up. I mean, this is definitely the way to do it, isn't it? So of course I need to leave it running for a little while. We still need to warm up the big hefty crystal oven. It's using 60 watts still. So it's far from being completely warm and all that. So there's of course no calibration or no messing around with anything. And I can see it's moving a little bit here. I don't know exactly what kind of frequency this one can do at its maximum. I needed to put sensitivity all the way up. See, otherwise it's not getting anything here at the higher frequency, so maybe we are close to maximum, but there is a little lamp here that can go over. So is that over what? I mean, what if I go here? See, this is the overflow. So you can of course do overflow in this readout here and get another digit. But here, I don't think you can you can go that fast with this type of technology. But we should probably just try and give it double the input power and then crank up the megahertz. Ooh, that was something. Oh, here we go. A little bit bananas. Let's try and give it some more input. No. This is 32 megahertz and that is not working. Let's go back to, yeah, okay, 30.3. And that is exactly what I have on my generator. So it can do 30. It can also do 31. No. Okay, so it can do 31.5. Maybe. So now I'm negotiating with the last digit. Ah, who cares about that? Yeah, okay, it can do that. Isn't that just beautiful? I think I want to play a little bit with the start, stop, and interval and all these kinds of things. But it was a lot of fun to at least have the frequency counter modes up and running. And that is the most essential. I really love this readout now. It's nice and clean. You can really see this from a big, big distance. And I'll leave this running and see when it's going down. It's still, yeah, about 60 watts. Okay, and period also works. And we have 1 kilohertz input. And it says 1000 microseconds. And I am using the 1 microsecond counter here. So that seems to be working. If I put it in up to 10, obviously it's going to go 10 or 100. So look at that resolution we have here. So this is very useful for lower frequencies. Let's go back to like 10 hertz, for example. Why is, this is because I have a waveform. square wave should be a more. So there is something. Why is it jumping so much? Aha! That is what I wanted to see. So this is 10 Hertz. And then I can overload. How about that? I think all the different modes works. I've been playing around with this for a little while now. I must say, the more I play with it, the more it's getting funny. See, B to C pulse is the mode. And here's our clock generator. So now B and C is here, right? And we are in microseconds. We can, of course, change milliseconds and seconds, right? Let's go back to milliseconds and reset, and then top. See, this is the milliseconds, and every time I push B, I start it again. Chup. Maybe this. Ah, look at that. And then it's ready. Chup. How cool is that? And then I can give it some more time. Start and then stop. And then it will save that. And then it will reset it after this time is running out. I totally love it. This is the coolest Nixie timer I've seen in I don't know how many months. Damn, I'm happy about this one. We got different triggers and all that kind of stuff. We got the output of the 1 mega. Wow, man, I'm happy. Anyway, I really don't want to say so much more about this thing for now. So I want to say thank you very much for watching, and I hope to see you soon again. Bye bye.